Okay, in this file, we want to then deal with the most general case. The most general case happens when the source could be at rest, it could be moving to the right, it could be moving to the left, and the detector itself could be moving to the left, it could be stationary, or it could be moving to the right. So any one of these possibilities represents, we need to see how to deal with this general case. So we already discussed this before in the previous video, what happens when the source moves and how the movement of the source results in the wavelength being shorter than it would have been if the source was not moving by this amount. So if you didn't read this, see this part, please go over the previous video. We already did this in detail. This part is not going to be different because this completely depends on the source, and once it emits the waves, the wavefronts move with that same speed VW. The distance between the wavefronts stays the same, lambda prime. So this part is completely exactly the way we did it, what happened before. Now we just need to see what happens on the detector side when the detector moves. And so let's look when the first wavefront arrives at the detector. Let's say that's time 0. And then after some time td, we defined the time between the arrival of the successive wavefronts by the detector, the perceived time. We defined that to be td, so that's the time when the detector, the second wavefront hits the detector. But the thing is that during that time, the detector itself has moved because the detector now is moving with the speed vd. So during that time td, how much distance has the detector moved? It moved speed times the time. So that's the time at which the second wavefront arrives at the detector, but the detector itself has moved. Okay, so what is the total distance then that the second wavefront moves during that time? It's the distance between here and here, right? So all this time, well, the second wavefront is moving with the speed vw, and it moved for a time td, so the distance is the speed times the time. So we can then find a relationship between this distance, and this distance, and that will give us, in the end, a relationship between the perceived frequencies. And remember, before we do that derivation or that those equations, let's remember that the detector, I'm assuming it doesn't affect the wave in any way. I mean, the wavefronts still move past the detector with the same wavelength they had before. So I'm just assuming that the detector is detecting, but it doesn't interfere with the wave in any way. Maybe that's an idealization, but it's not really important for the derivation. So let's see. So this TD VW is this whole distance, and it's equal to what? It's equal to this distance plus this one. So that's where we got this equation from. But lambda prime, we already know what it is. It's lambda W minus VSTS, and lambda W is VWTS. See the previous videos for that. We did that in detail. So when you substitute what lambda prime is from here, you get this equation. And you can see here that you have TD and TD, bring them on the left side, and you have TS and TS, bring it on the right side. Take it as a common factor on the right side. And then if I take 1 over the two terms, you get this. Why did I do 1 over? Because 1 over TD is just the frequency, FD. And then I can move this term up there. And 1 over TS is FS. And so we get now the relationship between the frequency of the source and the perceived frequency by the detector. It's modified by this factor here. The factor involves both the detector speed or the detector velocity and the source velocity. So that's the final equation that relates the source frequency to the perceived frequency by the detector. Okay, if we look at this formula and you see the part in red is the same formula that we had before when the detector was at rest. So when the detector is moving, you have this extra term here. Now, intuitively, when the detector moves to the right, then the time between successive wavefronts that it feels will be longer. So the frequency should be shorter. So when VD is positive here, you get something minus something smaller, and so of course the frequency then will be lower as expected. Now, if the detector is moving to the left, then it will feel the wavefronts faster, so the time will be shorter, then the frequency should be higher. And that's exactly what you will see here when VD is negative, then you get negative, negative is positive, and the frequency is a bit bigger. And so that's basically, this formula then takes into consideration all the possible movements of the detector and the source. So as I said previously, this formula takes into consideration all the possibilities if the detector is moving to the left or to the right. For instance, here we have two situations where the source is moving to the right, but in the case where V detector is to the left, then the frequency is higher, and when the detector is moving to the right, the frequency is lower. So this is just kind of an image that shows that. And we said that the intuition of that is that when the detector moves to the left, the time between successive wavefronts is lower. That means the frequency is higher. And when the detector moves to the right, the time between successive wavefronts is higher, and so the frequency is lower. And so if you put VD to be positive and negative, you get that in the equation. You get the same thing in the equation. So just to summarize again, this is the situation we have if the source is moving and the detector is moving. This is the equation that relates the frequency of the detector to the frequency of the source. By this factor, the Vd, the speed, the velocity of the detector could be positive or negative. The velocity of the source could be positive or negative. You have to put it with its sign, and when you put it with its sign, it'll give you the correct change in frequency, depending on if the source is moving to the right or the left, or if the detector is moving to the right or to the left. So what if we put like very special circumstances? What if we put the detector speed to be positive and to the right, and the source also to be positive and to the right? What will happen to the frequency relationship? Well, if you put here V positive and here V positive, you get this fraction becomes 1, and so you get the frequency is exactly the same. And so that means that what's happening here is because the source moves to the right, that makes the wavelength shorter, yes, but because the detector is moving to the right also, the time between successive wavefronts that hit the detector becomes longer, so it makes the frequency want to be shorter. So you have two things that are opposing each other exactly, so they cancel out, and you perceive then the frequency is exactly the same. Okay, what if we do the opposite? What if we put the velocity of the source to be negative and the velocity of the detector to be negative, but exactly the same velocity? So then you'll have here plus V and plus V. The factor again is equal to 1, and you get the same frequency. So when the source moves to the left, the wavelengths get longer, yes, that's true. And when the wavelengths get longer, then the time between successive wavefronts gets longer. That means, in principle, the detector should feel lower frequency. But because the detector is moving to the left, then the time between successive wavefronts is reduced, and so the frequency is higher. And so the two things exactly compensate to make the frequency exactly the same. Okay, let's look at this special case. What if the source is moving to the right and the detector is moving to the left? This is the case where you'll get a maximum frequency increase. Let's just intuitively see why. And you think about it also from the drawings that we did before. When the source moves to the right, the wavelength gets shorter. So then, in principle, if the detector is at rest, it should feel the wavefronts come to it, the successive wavefronts, in a shorter amount of time, so the frequency will get higher. But now, since the detector is moving to the left also, then the time is even shorter than that between successive wavefronts, and so you get the maximum frequency increase. And so if you can see what we can rewrite this formula for that special case when VD is negative, a negative number can always be written as minus magnitude of VD. So if you write VD as minus magnitude of VD, you have the minus and minus gives you plus, and you can then, the numerator becomes plus magnitude of VD. The source is positive, so you can write it as plus magnitude of Vs, but you have a minus, so it becomes minus magnitude of Vs. So this gives you the maximum increase in frequency. The numerator is increased and the denominator is decreased, which makes the whole term bigger the maximum possible way. Okay, what happens when the opposite case, where the source is moving to the left and the detector is moving to the right? Well, just intuitively, since the source is moving to the left, the wavelength that's created, the waves that propagate, have a bigger wavelength. So if the detector was at rest, it would feel the successive wavefronts hit it with a larger time. That means the frequency is lower. But now the detector is not at rest, it's moving to the right. And so the successive time between successive wavefronts is even longer than that. And so the frequency is even lower than that. So the two effects help to make the frequency the maximum decrease in frequency, or the least frequency that you can ever get. And so if you can see, if you put VD to be positive, magnitude of VD, because you have a minus here, you have minus magnitude of VD, and Vs is negative, so I can put it as minus magnitude of Vs, so minus and minus gives you positive here. So you get a decrease in the numerator and an increase in the denominator. So this becomes the smallest quantity it can be. And so the frequency is very small in this case. Okay, what happens if the detector moves with a speed that's close to the wave speed? Then what would the frequency be? You see that VW minus VW is 0, so you get a frequency of 0. Now, how can we understand that intuitively, what's happening? Well, this video or animation shows what happens when the detector moves with the same speed or close to the same speed as the wave. Look and see what happens. You can see that because it's moving with the same speed, then the time it takes for successive wavefronts to hit the detector is basically infinite. And so if the period is infinite, then 1 over the period is 0. And so the frequency is 0. So these are some of the special cases that you can find for the general case. These are some of the special cases.